Welcome to the Deep Dive. We're here to unpack those big ideas that are quietly running the show behind the scenes. And today, we're focusing on one particular moment. And one scientist who maybe almost accidentally found this key, this secret rhythm to how reality actually works. So our mission for you today on this deep dive is to really get a feel for why the universe seems to have this fundamental beat, this precise, almost musical quality. And how one scientist, who was actually pretty reluctant about the whole thing, uncovered this really profound truth. It's a story that basically rewrote physics, even though, well, he didn't mean to. Yeah, here's the core of it, really. Max Planck, he wasn't trying to start some big revolution. He was actually trying to save the old physics, classical physics. But in trying to patch up this gaping hole in understanding, he introduced a constant. And this constant, it really became, you could say, the metronome of the microscopic world. So we're going to unpack what that constant is, why it's so important, and how it's, quietly affecting your life every single day.
From the screen you might be looking at to, well, the super precise tech that guides us. Okay, so let's set the scene. It's 1900. Physics has this major headache. They called it the ultraviolet catastrophe. Sounds dramatic, right?
It was pretty dramatic for physicists at the time, yeah.
So imagine this ideal thing, a black body. It perfectly absorbs and emits all radiation.
Right, like a perfect little oven cavity.
Exactly. And classical physics, the physics they knew and trusted, it confidently predicted that this black body should just pump out infinite energy at really short wavelengths.
Like ultraviolet light, X-rays, just going up and up forever.
But the experiments, they stubbornly showed the complete opposite. The energy level went up, peaked, and then
gracefully rolled off, yeah. No catastrophe in sight, just nice curves.
A massive, undeniable contradiction. The theory just didn't match reality.
It absolutely didn't, and that's where Planck steps in. Not with some grand new theory, really, but with what he himself called, pretty openly, a desperate mathematical trick.
A trick? To do what?
Well, just to make the math fit the data, to make the theory match what they were actually seeing in experiments. He introduced this, well, really radical idea at the time. Energy isn't smooth and continuous. It doesn't flow like water.
Okay, so how does it flow?
It comes in chunks, discrete packets. He called them quanta.
Quanta, okay.
He proposed that the energy, let's call it E, of one of these little oscillators inside the black body could only be a whole number, like 1, 2, 3, never 1.5 times a tiny, tiny constant, which he called H, multiplied by its frequency, its rate of vibration.
So E-A-N-H-E.
Exactly. E-H-N-H-E, where n is just an integer. And suddenly, with that one assumption, the black body curve predicted by theory matched the experiments perfectly.
But the amazing thing, or maybe the ironic thing, is how much he disliked it. He thought it was just
bookkeeping, yeah. He said that. He thought it was a mathematical fudge factor, something needed to get the right answer, but not, how nature really worked.
He was trying to fix the old house, not build a completely new one.
Yeah, precisely. He wanted to preserve classical physics, but what he thought was just convenient accounting turned out to be, well, ontology. It turned out to be a statement about the fundamental nature of reality. And, this is where an approach we call motion theory can offer a really interesting way to visualize why this had to happen.
Motion theory. Okay. How does that help here?
Well, think about any vibrating system, like a guitar string or a light wave bouncing in that black body cavity. Motion theory helps us picture these not just as waves, but as closed loops in something called phase space.
Whoa, hold on. Phase space. That sounds a bit abstract, maybe a little sci-fi. Could you break that down for us? What exactly is a closed loop in phase space?
Yeah, it sounds fancy, but the idea is actually quite intuitive. Think of phase space as just a special kind of map for anything that's moving or changing.
Okay, map.
Instead of just tracking where something is, its position, this map tracks both its position and its momentum, how fast it's moving and in what direction at every single instant.
Ah, so it's like a dynamic map, position and motion.
Exactly. So if you have something that repeats its motion, like a pendulum swinging or an atom vibrating, it traces out a path on this map. And if the motion is stable and perfectly repeats...
It makes a loop, coming back to where it started on the map.
Precisely. A closed loop. That signifies a stable, repeating, coherent motion. Now, here's the key insight from motion theory. For these stable motions, these closed loops, to maintain their stability, their coherence, they can only exchange energy in specific ways. They have to make whole turns of phase.
Whole turns, like a full rotation.
Kind of like that, yeah. Imagine a dancer doing a spin. They can do one full spin or two or three. Those are stable, complete moves. But trying to do, say, half a spin and just stop, It's awkward. It's not a naturally repeating thing.
Right, you'd lose your balance.
Exactly. So these loops in phase space, they need to complete these turns. And the smallest possible turn, the most fundamental unit of this change, what we call action, that these loops can exchange and still stay stable, still stay in sync. That's Planck's constant, h.
So h is like the minimum viable spin.
That's a great way to put it. It's the minimum chunk of action required for a stable exchange. So the ultraviolet catastrophe, from this view, was basically a budgeting error. Classical physics was trying to assign energy in amounts smaller than h to those high-frequency vibrations.
I know it's too small to make a whole turn.
Right, amounts that couldn't form a stable, discrete packet, so those vibrations just couldn't stably hold that energy.
Okay, that helps visualize it.
Yeah.
So if h isn't just some number Planck plugged in, but this fundamental action quantum, this minimum turn, what is it really measuring? What does this metronome actually count?
Fundamentally, h measures the minimal phase area, that area enclosed by the loop on our phase space map, that a stable repeating motion can gain or lose without completely falling apart, without losing its coherence.
Phase area. Okay.
Any change smaller than one cell of this h area, and the motion effectively can't keep time. It can't maintain its rhythm. It just dissolves, essentially.
Like trying to play just a tiny fraction of a musical note, it wouldn't resonate.
Exactly. It doesn't work. And this view really illuminates that famous equation, E equals high.
Right. Energy equals h times frequency.
In motion theory terms, frequency isn't just cycles per second. It's literally how fast that loop's phase is winding around in phase space.
Okay. The speed of the loop.
And energy E is like the pressure or the drive that makes that phase wind. So when a system exchanges 1 unit of energy, high, it means it's adding or subtracting exactly 1 extra turn's worth of phase per period for that specific frequency loop.
Wow. Okay, that's very specific. It's locked together.
It's incredibly precise. It has to be, because of this need for the phase to lock coherently. And it connects beautifully to momentum, too. You know, the other key quantum relation involving HP equals momentum equals h divided by wavelength.
Okay.
Here, momentum p represents a spatial phase gradient, how quickly the phase changes as you move through space, and wavelength is literally the phase spacing in space, how far you have to go for the phase to repeat.
So shorter wavelengths means faster phase change.
Steeper gradient, exactly. And that means higher momentum. It all fits together through the geometry of these phase loops. So the unifying idea here is structured motion. Any stable repeating pattern trades in quanta because phase lock demands it. It's not arbitrary. It's fundamental to maintaining coherence and rhythm in the universe.
Okay, that phase lock demands it phrase really lands for me. It makes h feel less like just a number and more like, the fundamental size of the note in the universe's music. If you don't hit that note size, the whole thing falls apart. And clearly, this wasn't just about fixing that black body radiation problem. This idea, this constant h, it just rippled outwards, didn't it? It became the foundation for almost everything that followed in quantum mechanics.
Absolutely. Planck maybe reluctantly planted the seed, and it just bloomed everywhere. Think about the photoelectric effect.
Einstein, right, shining light on metal.
Exactly. And Einstein explained it by realizing the light itself comes in these packets, these photons, each carrying high energy, and you need at least one whole quantum, one packet with enough energy high to knock an electron loose.
You can't just gently nudge it out with less energy, even if you shine more light.
Nope. You need the right size ticket to get that electron out. It's a quantum transaction. Or think about the specific heats of solids, how much heat they can store.
Right.
At very low temperatures, classical physics predicted they should keep storing heat, but they don't. Einstein and later Debye showed it's because the vibrations in the solid, the atomic lattices, they also have quantized energy levels based on h. When it gets really cold, there isn't enough thermal energy around to excite even the lowest high vibration mode.
So the loops literally can't accept the small change of energy.
Exactly. The thermal orchestra can't play those notes because the minimum energy required high is too high compared to the available thermal energy, kT. And then you have Niels Bohr's model of the atom.
With electrons orbiting like planets.
Well, that picture evolved, but the key idea Bohr introduced using h was that the electron loops, or orbits, had to be quantized. They had to close with an integer phase count, effectively meaning their action had to be a multiple of h to be stable. That's why atoms only emit specific colors of light, specific frequencies.
Because the electrons can only jump between specific energy levels, releasing specific quanta high.
Precisely. And then there's Compton scattering, showing light behaving like particles bouncing off electrons, and de Broglie's radical idea that particles like electrons also have wavelengths, OHP.
That matter is phase you can push. I like that.
Right. It all comes back to H. All these different phenomena, they all, as you might say, rhyme with Planck's first cut, no sync without quanta. It's the underlying rule.
So, okay, this isn't just history or abstract physics for the lab coats. This gets very real. What does this mean for you listening right now? Where does Planck's constant, this H, actually show up in your world?
Oh, it's absolutely everywhere, especially underpinning the precise technology we rely on completely. Lasers are a perfect example. Think of a laser as a kind of domesticated Planck machine. You pump energy into a special material inside a cavity. Nothing much happens until a specific light wave mode, a specific frequency reaches a threshold. Then, boom, the atoms release their energy as photons of exactly that frequency, high, all in lockstep, perfectly synchronized.
That's what makes laser light so coherent and pure in color.
Exactly. It's quantum mechanics harnessed. Or think about LEDs, the lights in your screens, your lamps, and solar cells, too.
Okay.
They work because of something called semiconductor band gaps. These gaps are energy differences, and electrons have to jump across them to emit light in LEDs or generate current in solar cells, and the size of that jump. It's dictated by quantum rules involving H. So the color of an LED is basically a strict frequency contract enforced by high.
So the specific energy gap determines the specific high, the specific color.
Precisely. It's quantum accounting. And it gets even more fundamental. Look at superconductors and the Josephson effect.
Right, where current flows with zero resistance.
Yeah, and when you put two superconductors close together, you get these amazing effects where the quantum phase difference between them generates incredibly precise voltage and frequency relationships, all directly proportional to H. It's like Planck's constant signing your metrology. Our entire system of electrical standards relies on this effect now.
Wow, okay.
And there's the quantum Hall effect. In certain materials under strong magnetic fields, electrical conductance doesn't change smoothly. It jumps between perfectly flat plateaus. And the values of those plateaus, they are exact integer or fractional multiples of H and the electron charge squared divided by Planck's constant.
It just shows up again, unavoidable.
Unavoidable and exact. The topology, the fundamental structure of the electron motion in that situation, makes appear with incredible precision. It's now used as another fundamental standard. In fact, even how we define the kilogram changed radically in 2019. We ditched the old metal cylinder and
The standard kilogram.
Yeah. Now, the kilogram is defined indirectly by fixing the numerical value of Planck's constant H. We use a device called a Kibble balance, which relates mass to electrical measurements that depend on the Josephson and quantum Hall effects, ultimately tying mass to H.
So H is literally the bedrock for mass now.
It's the bedrock. So bottom line, almost any truly precise technology you rely on, GPS timing needs atomic clocks based on high transitions, high-speed fiber optics depend on lasers and precise frequencies. MRI machines use nuclear spins quantized via atomic clocks themselves. They all spend Planck's constant. It's the hidden currency that makes modern precision possible.
That's really astonishing how one sort of reluctantly discovered constant just permeates everything. But, quantum ideas can still be really confusing. A big question people might have is H just like a convenient number we invented for our math, or is it really real, part of the fabric of the universe?
That's a really important question to ask, and the answer from physics is a very strong no. It's absolutely not just a mathematical convention or a convenience. It's real.
How can we be so sure?
Because we can measure it, and not just in one way related to Planck's original black bodies. We can measure H in, I don't know, maybe a dozen completely independent ways.
Right.
Like looking at the slope of energy versus frequency in the photoelectric effect, measuring the voltage-frequency ratio in the Josephson effect, measuring those conductance plateaus in the quantum Hall effect, analyzing the wavelength shift in Compton scattering, measuring the frequencies emitted by atoms, looking at the diffraction of electrons, all these completely different experiments, different phenomena.
They all give the same value for H.
Exactly the same value, down to incredible precision. That kind of agreement across so many independent methods isn't an accident. It's not a convention. It's, you could say, the substrate signature. It's a fundamental property of the universe telling us how it works.
Okay, point taken. H is real. It's fundamental. But If everything is ultimately quantized, built on these h-sized steps, why does the world look so smooth and continuous to us? Why aren't we seeing tiny jumps everywhere?
Yeah, that's another classic and excellent question. Why don't we perceive the quantumness directly? The main reason is scale.
The steps are just too small.
Incredibly small, yes.
Right.
But also, in macroscopic objects, things we can see and touch, there are just so many of these quantum systems, these little vibrating loops or energy levels, and their individual height spacings are often tiny and incredibly close together. So what we perceive is the average behavior of literally billions upon billions of these quantum systems. It's like looking at a pointillist painting from far away.
You don't see the individual dots, just the smooth image.
Exactly. The many loops with the tiny high spacings blend into smooth bands. Microscopic systems effectively smear the quanta into continua for our perception. The underlying graininess is there, but it's far too fine for us to see directly without very sensitive instruments.
Okay, that makes sense. So the world is grainy but looks smooth. Does this quantization, though, mean that reality itself is constantly jumping, discontinuously, like teleporting between states?
That's a subtle but important point. Does quantization mean everything is jerky? Not quite. It's more about the exchanges.
The transactions.
Right. Quanta, these h-size packets, describe the allowed units for interaction or exchange between these structured systems, these loops. When energy or momentum is traded, it happens in these discrete lumps.
But what happens between the trades?
Between those discrete exchanges, the state of a system, like the phase of that loop we talked about, can actually evolve smoothly and continuously according to other quantum rules, like the Schrödinger equation.
Ah, okay, so it's not like reality is a badly edited film jumping all the time?
Not necessarily. Think of it as discrete trades plus continuous evolution is the everyday world. The interactions are quantized, but the state between interactions can change smoothly. Understanding that nuance, that it's primarily about the discrete nature of exchange, is really key to getting the right feel for this quantized beat.
That distinction helps. It's less jarring somehow. Which brings us back to Planck himself. It really is one of the great ironies, isn't it? This man, by all accounts, was deeply conservative in his thinking, meticulous, rigorously classical.
Absolutely. Very careful, very thorough.
And he dedicates his life to upholding classical physics, and yet he's the one who ends up planting the quantum seeds that just completely revolutionize everything he believed in. He must have felt conflicted.
Immensely conflicted, especially early on. But he was also incredibly honest. If the math and the experiments pointed somewhere, even somewhere uncomfortable, he felt obligated to follow. He wasn't one for grand, speculative leaps. He wanted the physics to be grounded in observation.
And there's more to him than just the physics.
Oh, definitely. He was apparently a gifted musician, a pianist, even composed symphonies when he was younger, a dedicated teacher, very respected. But also, his life was marked by terrible personal tragedy.
I remember reading that he lost children.
Yes, sadly. He lost his first wife, and then all 4 children from that marriage met tragic ends, including both sons dying in the World Wars. It's hard to imagine enduring that.
Good grief. Yet he kept working, kept contributing.
He did, and through it all, he maintained this profound insistence on, let's say, measurement over metaphysics. His approach was always, let the experiment speak. Make the motion talk, as the motion theory perspective might put it. Don't impose philosophical ideas. See what the physical world actually does.
Even if what it does feels weird.
Even if it feels weird, that intellectual honesty, even when it led him to a quantum theory he initially resisted, is really a powerful lesson.
So let's wrap up this deep dive. Max Planck, this reluctant revolutionary, essentially found the universe's minimum admission price. The smallest ticket you can hand a resonator, like a vibrating atom, and still be heard. And that ticket price is H.
That's a great analogy.
He was, in a way, a boring, stubborn, universal kind of genius. Not flashy, but the change he triggered was absolutely fundamental.
That's exactly right. And bringing it back to that motion theory synthesis, Planck's discovery really gives us the fundamental rule governing all stable, structured motion in the universe. Loops must trade in whole phase quanta to remain coherent.
One rule to rule them all, almost.
It sounds simple, but think what it explains. That single sentence, rooted in H, tells you why the light spectra from atoms don't just explode into infinite energy, why atoms themselves are stable and hold together, why laser light is so incredibly narrow and precise, why our definition of the kilogram now rests on quantum effects like Josephson junctions and Hall bars, and ultimately why no measurement, no interaction with the universe's rhythm ever comes completely for free. There's always a minimum H-size cost.
So here's maybe a final thought for you. listening, to mull over. Planck didn't set out to make the world weird. He wasn't asking for strangeness. He was just asking the universe to be consistent with what we observe, with the measurements. And the universe's answer, it was quantization. It was this reality's own elegant, incredibly precise way of paying for rhythm without losing the beat. It was always about motion, about vibrations and cycles, and Planck just revealed the size of the note that this cosmic music requires to hold together. Hopefully, after this deep dive, you're feeling a bit more attuned to that synchronized, quantized rhythm humming beneath everything.